Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
What's going on, everyone? It's Jaron from Jeranism, back with another live video for you today. Thank you so much for joining me. We are ahead of it. We got a treat ahead of us, so I'm excited. I love these presentations. Sometimes we get to learn something from some other people that maybe don't get enough views on their channel. Maybe their videos don't get enough views, and when I see them and think they're good, hey, invite them on the show and let them present to you guys, and you guys can decide for yourself if you think it's anything interesting or worth noting. I think tonight or today or wherever you might be, we might be in for a treat. So first off, I want to say thank you to all my patrons. Of course, as always, if you want to join them, you can do so easily. Patreon.com/Jeranism. Support what you like so it doesn't go away. Tonight's show is called A Concept for Vision, Bottom First Disappearance Across Flat Surfaces. And my guest tonight, or the person that's going to be giving the presentation, is Travis from Life is Short. What's up, Travis? How are you?
Hey, Jaron. How's it going? Hello, everybody.
Good. I'm glad you're back. I think a lot of people enjoyed the last time you were on my show. We did a good video, or you did a good presentation on refraction and all that fun stuff. I thought it was great, and I hear people comment on it all the time, or bring it up and say that they really enjoyed it. It helped teach them something. So I'm hoping kind of the same thing for tonight. So let me transfer over to your screen. Here we go. There we go. I believe you're on. So I guess you could just start out by telling people, who you are. Actually, what I should do is show your channel. I'll do that first. Just tell people who you are, what you've been doing. And I have a question of, you're obviously good at math. Do you have some sort of background in it, or you certainly seem to know it pretty well. So why don't you tell people a little bit about that? Yeah,
sure. I've been doing flat Earth kind of stuff, or at least looking into flat Earth since around, I guess early 17, somewhere in there. Mm-hmm. And then some of the channels that are out there, namely, Nathan, Ranty, Bob from Globebusters, Eric Dubay, all the typical folks kind of made some good arguments and put some things out that made you scratch your head. And then from there, I just started trying to figure it out on my own, what I believed to be true and not true. And here I am, I guess. And as far as science, I have a science background. I probably won't go into it much more than that, but I have a lot of years of education, and so, but it doesn't matter. Anyone can do this stuff. This is not, most of this stuff is basic trig. I just ask people to think critically about some of this stuff, because some of these arguments are real killers. So for what the model that was put forward.
I agree. Yeah, so I'm showing your channel now. People can, scroll down in this video if you want to follow the two links. There's two links there. One link is to the video, A Concept for Vision, Appendix A, Bottom First Disappearance Across Flat Surfaces, which is a great video from February 6th, a little more than a week ago. It's a good video. It's only, about 25 minutes, pretty quick watch if people want to check that out. But that's the video I watched and then said, let's have Travis on to kind of talk about it a little bit, so you can watch that video if you want. It's in the description. Also subscribe to his channel and check out, if you haven't yet, his video. You'll see here, I pulled it up on the screen. It's Angular Resolution and Our World. It's about 3.5 hours, and if that's too long for you, you can break it up into little bits. If you go to his channel, you'll see right after that he released it in 6 different parts, 1 of 6, 2 of 6, obviously on to 6 of 6, and just giving some great examples. And like you said, think critically, think for yourself. Look at the information presented today and decide for yourself if it matches the model that we've been given. So that's basically it. And today's presentation is A Concept for Vision, Bottom First Disappearance Across Flat Surfaces. So let me go ahead and bring up your screen now, and boom, there you go. Let's hear it.
Can you see my cursor on there?
Yeah, absolutely.
Okay, perfect. Okay, thanks. And I guess the other one too is if people can watch, the Angular Resolution one was my first one. And there's some things in there that I've kind of tweaked since then. So A Concept for Vision is the one that, which hasn't gotten a lot of views, but that's the one that I think is a little more definitive, and I think has some really good info in there. So, and this is meant to be kind of an appendix to that, and that one was meant to have basically 3 reasons why I think one could objectively say that things disappear bottom first. And so this video is meant to be kind of the appendix to that first reason, which is that It has something to do with the way we normally see the world.
Right.
And the other reasons can be refraction or just something being in the foreground of your vision, which I'll just briefly cover later. But so that's kind of the reason why this video was put together. So
Good. Yeah, because people I think fail to realize, that things can disappear bottom up for other reasons. Of course, the reason we always get is that's the reason that the Earth's a globe. Well, boats fly away, go away, and they disappear bottom up, and things disappear bottom up in the distance, and therefore the Earth must be a globe. But I think you've done great work in explaining other reasons that it could disappear bottom up, and not that it could, but does. So,
Right.
Go ahead. Can't wait to see.
Yeah, and I think I first saw the light disappearing example. I think it was on Nathan's, but that really got me thinking about what is going on here, because it kind of tripped me out a little bit. So I started doing my own hallway observations and seeing what happened. And so this hallway observation was one of the first ones here. People can kind of see it there on the screen. The light goes away well before the camera ever hits the ground. We're about 500 feet away or something like that, and we lose it. We're still 2 or 3 inches off the ground at this point. So something's going on there. And then you put up stuff like this, and people put out reasons. Well, that floor is curved, or that floor is uneven, or whatever. And all those reasons are potentially valid. It's hard for me. I'm not a surveyor, so it's hard for me to go verify one way or the other what is going on with that floor. I don't think that's the case, that it's a curved floor, but it could be. So that's a potential counter argument. Or is it that the floor is uneven, kind of bumpy, wavy, whatever here and there, and that's because of the way perspective works. Some of that unevenness in the foreground would obscure something further down the road. So that's kind of what spurred me on to this part, which is the appendix, right? So how can we verify this across a flat surface, or something that everyone would seemingly agree would be flat? And so there is a lake or a pond kind of nearby, and on a perfectly calm day with some still water, you can see the reflections are all pretty nice and perfect with one another. And I was taking the dog for a walk, so I started, and there was a piece of debris on the far end of the field over there on the other side of the thing. And I started noticing, obviously, it's disappearing as well. So I zoomed in on it. You can see that little white piece of debris right here. And then the bench right here. But you can just see this white piece of debris, and it's gone, right? Mm-hmm. So, and this water is perfectly still. There's no obstruction. No one could argue that this water is somehow wavy or uneven. So that was kind of interesting to me. What was also interesting to me was this little white piece right here. You see that white piece of debris?
Right.
That my pointer's on? So watch where that goes, right? So I'm right here. I'm like a foot off the water, okay? So watch how this approximates the line up here as I get lower. So it's going to go through the whole thing again. Sorry, it's Keynote.
No problem.
But we talk about that in a concept for vision, where your perspective ramps these things very quickly into the horizon line. It compresses things really quick into that line. So how far do you really see along that surface? So here's this piece of debris right here, where I'm pointing to, and it'll start here in a minute. And so you see where it goes. Gets right to that line. You see that?
Right. So
and that piece of debris is literally 15 feet away, right?
Right.
So anyway, I hope that makes an impression on people, that something 15 feet away can get that close to someone's horizon line. Now, when I'm up here at a foot, my potential, there's ground right here, right? Mm-hmm. So let's say I'm 2 foot off the ground. Well, my horizon is going to be somewhere about 2 miles away, mm-hmm. right? But obviously you're not going to see that because there's houses and other junk in the way. But as I get lower down, that horizon pulls in toward me, and I can't see that far along the surface anymore. And so that's why this thing gets way up onto my horizon line, and that's, I think, why this debris and all other objects start to disappear, is because they're just pressed lower into this I guess, gap of sorts. So
right. And I guess if there was other debris too, if there was more debris between that piece that you pointed out in the center of the screen right now and the shoreline, that would also disappear as we rose up.
Yeah,
or
absolutely.
As we go down, sorry.
So here's kind of some still shots of the where I'm about a foot off the ground and when I'm about, the half inch off the ground, and where that debris, how it went up into that line, right? Mm-hmm. So I want people to notice that that's what I'm pointing at here down to the bottom. But what I also want people to think about is that this is 400 feet away, right? Between the piece of debris and where I'm at is 400 feet. And so if this piece of debris, which is, let's give it like 15 feet, 20 feet, whatever you want to give it, it's pretty near, that gets all the way up to this point in the frame. That means that 300 and however many feet, right? Mm-hmm. Or let's say it's 400, it's close to 400 feet are crammed between this little white dot and this purple line, mm-hmm. right? Now, are you seeing all that information? No, you're losing information along that way.
Right.
So anyway, it's a function of how our vision works. The other thing that people have brought up, there's is this an obstruction in the foreground thing? And that's why this is a perfectly, from left to right, everything disappears, right? Mm-hmm. This isn't like some wavy phenomenon of refraction or an obstruction or debris that lost this debris that's on the far side of the lake, right? This to me is an aspect of our vision. This is how things work normally. Because there's been a lot of comments on things it could be this and it could be that. I don't think so in this case. That's why I did it across just 400 feet on a perfectly clear day with a very warm temperature that matched the water temperature. I don't think the refraction or any of those things come into play here. So anyway, so I believe this is a normal aspect of vision, and it seems related to our ability or inability to process information when we're near tangible surfaces like ground or walls or ceilings. There's nothing weird about this happening against the ground that doesn't happen against a wall or against the ceiling if we were to put ourselves against that surface and it was extending for a long period of time, right?
Right.
And I've done this on my own too. I found a really long straight wall, which is kind of hard to find. But I did this same thing, and you put the light up against the wall, and you get really close to the wall. And it's just like I think someone used the subway example. I forget who, maybe it was Zach, about if there were posters along a subway wall, and you get really close to that wall. All those, you're not going to see those posters anymore. Everything is going to get all flattened out. So. This nothing it's something to do with the proximity to a tangible surface that kind of compresses and then we lose information. And that's all I'm really saying, right? I think that's just a normal part of vision. It has nothing to do with the curvature of the surface.
Right.
Okay?
People need to recognize it in 400 feet, and you can watch this video for the exact mathematics on it, but there's no curvature to speak of, especially when you're talking about even the distance between your camera lens and the water. Certainly can't be any curvature that's covering in 400 feet. It would be negligible, and I mean centimeters. Right.
And we'll do that a little bit later. We'll calculate what this means to have the amount of obstruction that we had. Mm-hmm. What would that mean for a globe model for it to fit that narrative? And it's absurd. So how does perspective work? I'm not going to go into this too much because you and I covered this last time. But if you remember, we kind of talked about how far that cresting wave is and how perspective works and how it halves each time as you approach a horizon line. And so if you're looking at this from a 6-foot observer height and you're thinking to yourself, well, I can see 3 miles supposedly, how is that 3 miles broken up, right? Is it like this is the first mile and this is the second? Like where does that all start and stop, right? Well, it turns out that when you analyze this, and I've done this with all the hallway footage that I did using standardized the ceiling markers and the floor markers to see how exactly this works. And 3D software and everything does the same exact thing, where each iteration of a frame, you're doubling the amount of information in the next frame. And so when you do it this way, you find out that basically, and I had to blow it up so you could even see it, that this cresting wave is at this line right here, which corresponded when I did all my calculations to about a half mile away. And that kind of corresponds with all the other, if we go back in here, look at this, that 400 feet is crammed between this white dot and this purple line. It kind of makes sense. Most of the information that we see is crammed in the very upper lines right below the horizon. And so if you can see 3 miles, 2.5 miles is crammed. If you can see my cursor, 2.5 miles is crammed between this black line and this purple line, right? And that's crazy to think that you can actually see all the information that's probably in there. And it starts to make a little bit more sense now as to why information may start to get lost. But we went over that last time. So if people want to kind of look at that in a little more depth into how we arrived at some of these numbers and all that, they can look at that or look at a concept for vision. The other thing I wanted to note too is just look at how these numbers kind of ramp down into this plateau, and you can almost extrapolate a curve out from this, right?
Right.
And it's easy for me to see how people, if they weren't critical about what it is, how perspective seems to work, that they would have extrapolate out that this is all a curved surface somehow, taken to extremes, way out in here. But just think about how this seems to ramp up towards your horizon, and then if information is lost naturally, how it's going over the horizon the other way, right? Well, suddenly now you got a curved surface.
Right.
So anyway.
Yeah, I've heard him talk about perspective being halves and doubles. And, I don't know if people have heard that before, but it's exactly what you're showing there, that, twice the distance, and then you have to, half the amount. You can go ahead and show that. Yeah, exactly there.
Right. So you got 9 feet here in the next iteration. And this is the lower 1/4 of the entire thing. So this red line, from this red line down to the bottom of the frame, is the lower 1/4 of the total frame. It's the lower 1/2 of the lower aspect of the frame. And then you just keep having that. So from the red line to the purple line, now I half that and I get the orange line. And then I double the amount of information that's there. So this was 9 feet. This is 18 feet. And now from the orange line to the purple line, I half that and I get the yellow line. And now I got 36 feet in there. And then from the yellow line to the purple line, I half it and I get the green line. And it's 72 feet. And it goes on and on and on. So before you know it, in each one of these things, you're getting more and more information crammed into smaller and smaller spaces.
Right, and the way that he's proven this actually is by using floor tiles, that we know that, whether it's 12 inches or 16 inches, whatever the particular tile that you're looking at, but you can actually go into a hallway and show this to be the case. Yep,
that's exactly right. So we were able to do that, and I did that at each foot. So it's an 8-foot tall observation, and I go 8 foot, 7 foot, 6, 5, 4, 3, 2, 1, down to like 1 centimeter. And I show how in that field of view, how the information changes as you move up. And it ends up being this same exact thing. So when you go down real low, the amount of information that's crammed instead of 9 feet at a 6-foot observer height, let's say you're at a 1-foot observer height.
Right.
I forget what it is. It's not listed in here, but it's a lot less. It'll be, I don't even know. Let's say it's a foot, something like that. And so now suddenly that foot then doubles to this one. Now you're only seeing 2 feet in this next one right here, right? And then it's 4, and then it's 8. So instead of being 72 up here, you're looking at 8 feet or 20 feet or whatever, right?
Just by bringing the camera down. Yeah.
Before you know it, if you take the same iterations all the way out to the purple horizon line, you're not seeing as far, which makes a lot of sense. We don't see very far along surfaces the closer we are to them.
No, and I think people forget too. You always bring it up. It's a great point that the same thing would happen if we were upside down on a ceiling. All of a sudden, things would disappear very quickly on the ceiling, just like they do on the floor. It just so happens that we are near the floor, and actually, when you're talking about this, we're definitely closer to the ground than we are the sky.
Right. That's right. And you don't even have to be upside down, right? So look at along this ceiling right here on the left-hand side.
Right.
I'm now at 7 foot, and it was an 8-foot ceiling. So I'm now a foot from the top here. And the same exact thing happens, but just in reverse. So these red lines right here, all this stuff, this red line right here to this red line, there's a golf ball down here that's directly underneath the light that's right here. And then the next green line, that's a golf ball that's directly underneath the next green line, which is the next light. And they're each at 10-foot spacings all the way down. And so I did this to show how perspective changes as you alter your height. So if people can watch that, that's in a concept for vision, and you can kind of go through that. But anyway, that's how we arrived at the math and how this all makes sense, how this works in 3D software. You've talked about it before. So this is how it works. So now how things disappear and what happens at this point and how things get lost, that's the other question. So, but they don't go on forever. So that's the other, people who still believe in the globe it just keeps going forever. Well, no,
Right.
You don't see forever. So what happens? Well, perspective dictates that the ceiling meets the floor. So things go down from your top field of view and things rise up from your bottom field of view. So as something hits a near horizon in the bottom field of view, it will still descend along the top field of view. So it will appear as though it's disappearing bottom first. So I think if people aren't careful, they'll extrapolate out instead of a linear relationship between your height and how far you can see and how much information you're seeing. You can extrapolate out that curve, which is kind of what we just talked about. If you look at how perspective works and how it seems to ramp this exponential way, if you don't take into account the other exponential aspects of it, then you're going to extrapolate out a curve. So,
And a lot of people have said, I know Ranty and other people, that they've kind of reverse engineered optics into a curve, and that's exactly what you're pointing out there, that it's very easy to do if you don't scrutinize the information enough. You can easily reach the determination that, what we're seeing here is a curved surface. But when we go and do these observations on flat surfaces, it tells us that it might be a result of how we see, not the curvature of the ground we stand on, or lack thereof.
Yeah. Real briefly on this one, what I'm trying to say here is that essentially, if you don't take into consideration the fact that when something gets reduced in size by half, it has to be, twice as far away. Then if you just do this at regular intervals, you're going to get a curve. So you have to exponentially, if this guy is exponentially reducing in size, he also is exponentially increasing in distance. Mm-hmm. And that's why it's a log-log plot. It's not what they call a semi-log plot. The way we process the world, we think it's linear, right? That if I go twice the distance, the thing gets halved in size. But because a perspective is exponentially compressing things both in the field of view, in the vertical aspect, right? These lines are exponentially compressing to one another vertically, but also the distance that is contained within each one of those iterations is also on the horizontal axis. Those two together mean that it's a linear relationship between the two. But if you take one of them out and make it a linear relationship to an exponential one, you're going to end up getting a semi-log relationship and extrapolating a curve. So that's kind of conjecture for how I think maybe people are thinking about it the wrong way, but they just got to realize that this is a log-log plot. And so even though information exponentially compresses, it's compressing two ways, and so it's along a flat surface. I hope that makes sense. If not, don't worry about it. It's kind of a side plot. The other thing that's critical about vision is just, that it remains 50% of our vision. That when you get lower down to the ground, it's not that, whatever you were looking at maintains its position. The ground rises still to meet the floor the same way. Mm-hmm. And so as you're taking buildings or whatever, for example, and you're getting lower down to the ground, well, if you look at now, the buildings are all kind of on the same plane, but this aspect down here still becomes whatever's on the floor in front of you is still 50% of your field. So that's what I'm trying to show kind of here, right? You're down on the ground. This is still, you're just seeing a ton of tiles. That's taking up the majority of your vision, but it's still going to be 50% of your field. So, and I'm just kind of setting these things up that people need to kind of look at perspective a certain way. But I don't want to go through it in detail because I've done it for hours on the other things. So
right, people can check that out and
check it out.
I'll also link that video in the description. I forgot to, but I'll put in our last conversation because I thought it was good. A lot of people enjoyed it. But go ahead.
Yeah, I thought the one we did, I think, was a good a way of approaching some of that. So this is just, again, same thing we've been talking about, just kind of the golf balls and how it all seemed to work. And we've already kind of gone through this. I did pull out the line so you could see how these lines relate to one another. Remember, the red line is a golf ball on the bottom and the red line is the light on the top, but they're exactly the same distance away from the observer. And so then the green line corresponds to the green line again, yellow to yellow, pink to pink, blah, blah, blah. And so you can just see how your vision alters these things as we get closer to the ceiling and closer to the floor. Just something to think about. Kind of side views of that same thing. But keep in mind, when we got close to the floor right here, between this red line and where I'm at, it was roughly, I believe it was 12 feet. It could be, I'll have to go back and look. But not a lot of information is now crammed between the red line and it's taking up a huge chunk of this image. So again, things to think about with perspective. So how far you see is determined by your proximity to a surface, and it has nothing to do, in my opinion, with curvature. It has to do with how you can process information and how far and how long you can process that information for. And
people need to remember this is another, globe proof they constantly use, which is, if I get up on a mountain, I can see further. If if you're laying down on the ground, you watch a sunset. If you stand up, you can see the sunset again. These things are used constantly as proof of the curvature of Earth, and what we're showing you here is that no, it's a concept of how we see even on a flat surface.
Right. So, the good example here is, do you see a centimeter off the ground 400 feet away? Can I see a centimeter off the ground the entire length of this hallway all the way to the far wall, which is 400 feet or 500 feet away? And in my opinion, the answer is no. And if you calculate the how far you can see by resolution limit, then I can see roughly 95 to 100 feet away if I'm a centimeter off the ground. And that math seems to work out. So if I pulled the golf balls out and zoomed them in, and this is the 20-foot one, here's the 30-foot one, and then each one, right, and I get to 90 to 100 feet, which to me would be about the horizon, and here's a light. And this light is suddenly now starting to get obscured. You can't see a lot of this light anymore that was on the ground at the very about the 130-foot mark. So I think that is how this thing works. But people go out and do your observations and come up with your own ideas. But it seems to me that that's how far we can see. It seems to relate very closely to around 1 arc minute, which is a very average resolution limit for most observers. So it'd be what it is.
Which is about what, 0.02 degrees?
0.02 degrees, yep.
Right.
So if anyone knows the Buzz Dev, he's got a YouTube channel. I want to give him a special kind of shout out here because I think he's done some underrated work, and he's one of the guys. I think it was the Mount Rainier stuff that was floating around a couple years ago, or that was really throwing everyone for a loop because it was refracted or not refracted, but it was lower than it should be, and oh no, it's a globe again, and all this stuff. That's how I remember feeling, and I remember him doing a render. A 3D render with just adding refraction to a flat plane, and suddenly it looked exactly like the photo, and I was like, oh, this guy, I like this guy. So anyway, hold on.
No
dog,
problem.
I guess, wants out. But hold on one sec, Jared.
No problem.
But what I want people to look at here is just the renders between the photo on the left and what he was able to do with the 3D render on the right. So that's a CGI composite on the right of each of those photos, and what the actual photo is on the left of each one. And so the whole idea of this was we were going to try to show, do these 3D programs take into account this aspect of vision of bottom first disappearance? Do they render 400 feet away 1 centimeter off the ground or not? Mm-hmm. And so the answer we came to was it was kind of, I guess, a mixed bag, but because it's hard to determine how. I really wanted to know, does the computer program decide which pixel? How does it decide which pixel or voxel to remove, right? Because obviously you can't compress something forever, even in a computer program. So at what point does this thing say, okay, I'm going to remove these pixels now, or merge these into one. And I still don't know quite the answer to that. So anyway, hold on one second.
No problem. And I'll show everybody right now just so that they can see the video we talked about earlier, which is this one right here. And I'm going to grab the link for that. And let me go share, copy. All right. So I'll put this in the description. But this is the video we talked about: angular resolution, perspective, and refraction with Life is Short. We did a live presentation that was April 11th, 2019, so almost a year ago. But people should check this out. It was 2.5 hours, but it's great, and we're talking about a lot of the same things, but in a little bit more detail. So check that out if you want to get some more information that maybe you're missing from this particular stream. Anyway, just wanted to show people that.
Yeah, it was a good one. So this was one of his renders too. So in this one, he zooms in. So I zoomed in as well. Over here on the right is the 1 foot, and you can see it's really far away. But I tried to zoom it in as much as I could. And you can see the light right here. That's the light at about 130 feet away, at 1 foot off the ground, and then at 1 centimeter off the ground, that's the same light over here down in the lower left-hand corner. But you can see it looks a little different in the 3D render than, right? So it basically doesn't, it still keeps the light right there, which in reality did not seem to be the case. The light was very faint by this point, and in a couple instances it would just disappear. So in any event, so that again, this kind of background is what kind of spurred me on to think, well, what is it about the ground? Is this a normal aspect of vision, or was this a curved hallway, or a uneven hallway, or whatever? And so that's the impetus behind what the lake footage shows, which to me now I'm convinced that this is a normal aspect of vision. This is the horizon kind of gap scenario. So again, this orange line here is how far you can see along a tangible surface. It was going to differ from how far you can see along the other surface. And when you kind of collapse these things together and you put the ceiling where it meets the floor, they're not going to meet up at the same vanishing point. There's going to be this like an information gap kind of in the middle here. And I guess think that, these are the golf balls right here. So if you were to be looking at golf balls along that surface, when this information collapses, some of that information is going to get lost. That's how I view this. Mm-hmm. But again, keep in mind, this doesn't exist, right? We don't ever see the world in an orthographic side view projection. This is just conceptual to help people kind of, I guess, conceptualize what I think might be going on. We've done this one before. Again, just kind of showing the perspective lines within a hallway, and how as I get lower, if these were buildings or if they were, posters along a wall or whatever, they would do the same thing. And at some point, for whatever reason, every time the lights disappear along flat surfaces. So, and if we were to remove those walls and just replace the floor with the water, it would be the same exact. There's no reason to think that our vision changes from a hallway to standing up outdoors.
Right.
And I think that's an underrated argument that I hope people take home, that message. There's no reason that these disappearing acts along, short distance flat surfaces indoors is any different than long distances outdoors. Why would it be different? So, same thing here.
Only difference is we might be, higher up from the ground than we are with this camera, but it's exactly the same. And who else has done good work as far as this goes is Zachary Zabala, Good Times for All, showing these same kind of observations in his warehouse. So it's same thing.
Yep.
So
that's exactly right. And I referenced him quite a bit in my first couple videos because he did some lid observations in that warehouse that were really cool. So yeah, check out his channel for sure. And so again, same thing. This is just that Walmart example. We've gone through this. So again, you're on a Walmart floor, you blow away the ceiling and the walls, and why would suddenly your vision change and you stand up, right? Why would this horizon issue suddenly change to a curved surface over a ball when this is just a flat, let's say the Walmart was extended for miles, a cement Walmart for miles. Why would it change if you just stood up?
Right.
You still see the same exact effects. So same thing here, now we're just replacing it with a crop, some crops. It's just how perspective works. So there's another cool thing coming up, which I want to show some people. Well, I wasn't able to show it here before, but I want people to realize that I'm in a corridor right here, right? That's this kind of image. I'm in a corridor in a hallway, and I got my left and right walls and my ceiling and my floor. How do you get to the point of a horizon line in this scenario, right? So what I want people to do in their mind, I guess, is let's take a top-down view of this person now. So now I'm looking down on the observer, this blue guy, right? I'm looking down on the top of his head, and this is the left wall, and this is the right wall, and I'm going to pivot this wall away from this guy off of his vanishing point, way off in the distance here, okay? And I'm going to pivot it outward, and how would it look as I pivot outward? And so let's continue to pivot it outward. And what are we going to do? It's going to start to, these little yellow lines are going to get closer and closer together, and at some point they're going to be a line, right? And so if I were in a massive warehouse and I pivoted this wall away from me based on the furthest thing I could see, I would just be seeing basically a horizontal line and then butting up against the wall on my right-hand side, which is still over here.
Wow, excellent point. Yeah, I never thought about that. You're exactly right.
And then if I were to do the same thing now with the right wall and pivot it outward away from me from this point right here, I would be presented with a horizon line. So I'm just pointing out right here, what happens in hallways along the ground works similarly outdoors along the ground. There's no reason to believe we see the world differently outdoors. So this is your horizon line, but we got it from just rotating walls away from in a hallway. And I think this is really cool right here. So this is, again, special thanks to Martin from the Buzz Dev, because he created this for me. You see these little green dots right here along the way? Those are the golf balls, okay? And so he mocked this up basically based on the hallway footage. And then he took this information and then he rendered all the special effects on top of it, I think. But I asked him to do this to pivot the walls away from the vanishing point and to show people what it would look like. So enjoy this one. I think it's really cool. So now you're in a hallway, right? And now we're going to get down to the ground. So this is what it looks like in a hallway. We're going to pivot the walls away. And now you just have a horizon, right?
Right.
So I think that's pretty cool. And hopefully that makes it a little more conceptual for people. And notice too, I'll do it one more time. Notice too how the green balls approximate that horizon line and plateau really quickly. And now you're looking at them for a long distance, along a straight line ahead of you. And look at how much blue is right here, right? That's just these are all 10-foot intervals, and how much that took up your field of view.
And it's the same thing again with the halves and doubles from there. Yeah.
So pretty cool. All right. So here's the more measured, objective look at the lake footage.
It's a nice, clear night, perfectly still waters. I'll put the coordinates on Google for where exactly I am across this lake, and the distance of the light height, the distance of the light height, and the iPhone height. Bye.
So there's my mock-up there.
And so that's like a little flashlight. Is that what that is there, the blue thing?
Yep. It's a flashlight kind of hammered in, or that rig is kind of hammered into the ground in there to make sure it stayed exactly where it was.
Gotcha.
And then the little ripples are just where the case barely touches the water, right? It's just barely touching it.
Right.
I'm not immersing anything. I don't want to immerse my camera,
No,
right?
Don't do that. iPhones do not do well with water.
Yep. So there I am, just kind of stopping it, and here it is in some slow motion. So other people have said, well, if you zoomed in, you would have saw it. And that to me is a ridiculous argument. I can clearly see the thing at this point. What do you need zoom for? This is not a zoom issue.
Right.
So
I just think it's crazy, even when you look at how the little specks there, whatever those are, those little white things, how they ramp up all the way, and then they get to be the same height as the light, basically.
Right
below it.
Yep. So here's the points on Google. If people want to look at this in more detail, it's on the video. But it's basically 410 feet away. The iPhone height, just when the thing touched the water, it comes out to roughly about a half inch off the ground. And then I was being generous with I didn't even show the top of the light, which was at around 3 inches. I just went ahead and split the difference to about 2.5 inches, which is the middle of the light. So I get these numbers of my target being about 2.5 inches, my observer a half inch, and the distance being 410 feet. And so what I think was really cool that I didn't expect to see was at some point in the video, you can see it's autofocusing. And there's a little halo of light that as it's focusing, you can see this halo. But when you still the image, it's completely cut off bottom first, right? So some people could make the argument that, well, it just disappears. It's some kind of sudden effect of something. I don't know what. But this is a clear delineation of a bottom first, whatever it is that is obscuring the bottom of this thing is completely across the entire image. So I thought it was kind of cool to see this. It's sharply delineated. And again, this is not an issue of zoom. So if people are arguing that if I just zoom in, I now can see this entire thing, I think, it's a bogus argument. In my opinion, zoom only blows up what's already there. And so there's differences between fixed and variable aperture, zoom lenses, and all that stuff, and it actually gets really complex. But for the most part, zoom blows up what is already there in the image for you to see what was already there. It doesn't necessarily pull things that just aren't there in the first place into being seen. So I hope that makes sense a little bit. I've looked at zoom extensively, and it's kind of hard to figure out what the aperture is doing a lot of the time. So I've kind of put zoom on the back burner a little bit for now, but this is not a zoom issue. I'm not concerned that this is a zoom issue whatsoever. There's no reason. I can clearly see this light without any kind of zoom or resolution issues whatsoever.
Yeah, nor would the zoom really explain why we're losing it anyway. Right. Yeah. So if the horizon is the leading edge of a sphere with an R of 3959, what should we see, right? So if this is the water is curving, right? So let's say that I don't care what reason you come up with that why this thing is cut off bottom first. The predominant reason that's put forth is that things obscure because of Earth curve. Mm-hmm. And they never provide alternative reasons, because if they did provide alternative reasons, they would have to then account for those before they ever said that it was Earth curve causing something. Right, which they don't want to do that.
But they don't want to do that. So let's assume that this was because this water, this 410 feet of water, is curved Earth, right? So let's assume that. What should we be seeing? So you do the math on this, and it comes out to that what should I be seeing at this height? I should be seeing basically the entire thing, because my horizon, according to these maths, is 1,314 feet away, which is, close to 3 times the amount that it actually was, 400 feet away. And that the amount of drop that I'm supposed to be seeing is just 1.2 millimeters. Now, if you know how big a millimeter is, you'll understand how ridiculously small that is, right? And so that's the amount of curve or drop that is supposed to be present in this across 410 feet of lake, okay? So what they're saying is 1.2 millimeters is what's obscuring this entire light. Okay? That's the only thing I can...
Yeah, people need to
That's
just...
the only reason, unless they say, oh, no, well, it's because of some optical thing. Okay, great. That's what we've been saying all along,
Right, that's our point. Thank you for arguing our point. Yeah, and 1.2 millimeters is tiny. It's like an ant. Basically, is about probably 1 millimeter.
So I went to some of the famous Earth curve calculators to just verify see what they could say about it. And this is all in the video. But all of them have basically, this thing is not obstructed whatsoever. You should see the entire thing based on the size of the Earth. Mm-hmm. For all intents and purposes, this is flat water. Okay? Even on a globe, this is essentially flat. It's got a 1.2 millimeter drop. It's essentially flat, right?
Not 2.5 or 3 inches.
Right. Definitely not 2.5 close to 3 inches off the water, which is what this thing was.
Right. And obviously anybody who thinks that there's any kind of waves or anything, we're showing you that that's not even possible.
Right. That's why I did it on this night was that I needed this perfectly calm, still water, right? Mm-hmm. That way the obstruction issue would not come up. So, anyway, same thing here. This is just verification of how little, look at the bulge height, 0.3 millimeter of bulge height on this one, yet 2.5 inches were obstructed. More geometric results here, again, because they assume that you look down across a bulge of Earth, and that's why things obscure. That's how they modeled this out. So they either need to scrap this theory. Well, that's what they need to do. If they want to continue believing in the globe, they're going to have to scrap this geometric horizon issue.
Which is what we're seeing recently with a lot of the stuff coming up, a lot of the things that people are showing, and some of the videos Taboo's done, and the observations that Bo's done. With these platforms out in the water, they've got to scrap the whole idea of if we live on a sphere, then the horizon that we see is a physical edge because it's just not driving anymore.
Right. There's too much information at this point for them to pull that off anymore. Here's some more calculators again showing that basically nothing should be obscured.
We just got a super chat, by the way. Thank you, Sky Free. And Sky Free, people need to click while he's in the chat right now. Click on his channel. I've been showing a lot of his videos lately that definitely show exactly what's being shown here. And he says, we agree with everything said here. We've made similar observations ourselves and can confirm the info with the videos on our channel. Horizon equals horizontal. And then a thank you to Fish Matrix, who said, thank you, great stuff. Condemnation without investigation is the height of ignorance. And Flat Earth Vegan said, this is awesome. So thank you guys so much, and definitely check out Sky Free. I keep using his footage. Ranty keeps using it. He's just going out and making some of these short observations. I did it on a show I did earlier today on the Thursday live show, just showing his boat floating off in no man's land. And again, if you're to believe that the horizon is the edge of a sphere, then that boat is somehow floating up above it. But we know that that's not the case. The boat is actually on water, which tells you that the horizon is an apparent position, not a geometric edge of a sphere. Right.
Yeah. So if the horizon, so if we take this argument even further and say, okay, let's see what is the size of the Earth then if 2.5 inches is obstructed across 410 feet. Mm-hmm. What would be our size of the Earth? Well, there's a variety of ways you can do this, and you get some. I found the kind of the most reliable way. We'll just do the basic trig on this, and you come somewhere you average out to somewhere around 900 miles, or you could use the 8-inch drop per mile squared approximation. We'll just do it across 2.5-inch drop across 410 feet. Versus 8-inch drop across a mile. Mm-hmm. And you basically get around the same answer. So, but either way, now our R, by this argument that curvature is what obscures objects, our R is now 1/4 the size it should be, and the Earth is smaller than what the moon is told to be, right?
Right. So circumference of like 5,500.
There's far too much obstruction here for this to be curvature. So you can believe that, or you can believe that something else besides an R of 3,959 miles is responsible for bottom-up disappearance, right? Mm-hmm. And I don't care what reason you come up with, but it's something else besides this, right? and it's something that needs to be accounted for.
Right. It's something that's simply ignored because they just keep calling it Earth curve. Every time there's something missing in the distance, it's Earth curve, it's Earth curve, it's Earth curve. And, this presentation alone shows you that it's something else. You can believe whatever else you want it to be. You can come up with whatever ideas you want, but it simply isn't the leading edge of a sphere.
Right. And so that's how I came, that's essentially the nuts and bolts of it. So is information loss an everyday aspect of our visual horizons? Is it secondary to the distance from the tangible surface, the wall, the ceiling, the floor, whatever it is we're against? And so what I want people to focus on too is, I know we've talked about, people say, well, it goes off into the distance and it gets too small to be seen. The bottom of the boat gets too small. I don't think it's the bottom of the boat that gets too small. I think it's the ground. The ground shrinks in, right? Mm-hmm. That's to me what is happening. It may not be that the bottom of the object disappear from it being too small to see, because the bottom is going to be the same, it's going to shrink at the same rate as the top, right? That's just how perspective works. There's nothing particularly important about the bottom itself versus the top, of a boat, right?
No,
it's all going to shrink together as it moves away.
Right.
But what is important is the ground that it's on.
Right. One's definitely closer to the surface than the other.
Right.
And it's going to cause a loss of information because there's too much trying to be fit into that last little bit.
So I think the same thing that's happening, in our hallway example, in this lake example, and just standing up and looking at something on a beach, this is all the same thing. And so here, the nuts, why do we see in perspective? And this is something that I've kind of grappled with in my head. I know it may seem like a simple question to some people, but why do we see the world the way we do? Why does the floor meet the ceiling in the distance? Mm-hmm. Have you ever thought about that? I don't know other people have thought about that.
Yeah, it's a tough question, man. It really can lead you to why our eyes work that way. I've always wondered if other animals see the same thing. Is it just a product of lenses? Because obviously we see the same thing with cameras, but it's definitely an interesting question.
I don't know if it's a property of the way the light is projected to us or outward towards us, inverse square laws, and then take that plus the way the lens bends the light back in to be focused. I don't know. But I think it's an interesting question. So why do we see in perspective? People have come up with, and I discussed this with you, that the vanishing point was basically, the radius of the diffraction limit. The most smallest thing seen in the very distant, at the most distant point would be the point of like the origin, right? Of how the world was then projected outward towards you. And then you then converged all that information together. Mm-hmm. But I don't know. I still don't know. I went off on a big tangent. That's why I haven't made some of the videos lately, but a big thing about, gravity really threw me for a loop for a while. So I spent a good probably 6 months and I put together like 300 slides on gravity, what I thought about it, what it could be, whether or not it existed or needed to exist or not. And I'm just going to put that one on the back burner because it's just a hard question. And
yeah,
I don't know that there's enough information out there to come to a conclusion.
No, some things I think, I don't know. Some things are just the way they are, and it's hard to explain them, and maybe they're not even explainable. But I know people will always be out there trying to explain it, saying that it has to be this or it has to be that. But yeah, I've done the same thing, trying to look at it. And you said you had 300 slides on it, so I would be interested to see that video whenever you get around to at least putting it out, or just kind of some of your thoughts on paper to see what you think or what you found.
Yeah, I think I'll have to. What I came to the conclusion of was just that I couldn't prove any of it. It was just all conjecture and what I thought was kind of interesting, but not anything that I could say definitively one way or the other. So I felt God just really I didn't need to go that route because I don't know the answers to those things, and so I didn't want to lead anyone astray. Stuff on optics and everything else, I feel like it's kind of definitive, and I'm not telling anyone anything that I don't feel strongly, a strong conviction about. I think this is how the world works. So I feel good putting this stuff out. So this part right here, this is conjecture though, right? This is like, hey, This is just something I found interesting from my look into electric fields and all the, Bob is real big into this kind of the electric universe stuff, and I agree with him on a lot of that part. I don't know I agree with you, or I don't know that I agree with him on the gravity aspect. I think I might more agree with you now, and Nathan and everyone else, that we may not even need to have a force there if you take yourself into the position of the person in the ant farm. And the only time you actually may need gravity is if you take yourself out of the ant farm and put yourself into the position of God, right? And the orientation in which he put the world, right? With the direction he put the ground was where the ground was, and
Right.
and he put cycles above and cycles below that differed, and suddenly that's just how it runs. There doesn't necessarily need to be a force there. I see both sides of the argument. I just
and that's
don't know
kind of
the
where
answer,
I'm at too, and that's why I've tried to do more listening rather than speaking, because just like you said, I don't want to lead people astray either. What I want to do is just do more listening and more have an open mind to both sides. So I totally agree with you. I see both sides of the argument. I still stand behind mine, but at the same time, I'm open to the other and love to hear people explain why they think it, because it just helps me get a better understanding. But I've come to kind of the same conclusion that you have, that it's really open for interpretation, and it kind of depends on what you're looking at. And I don't know if there's variables that we can remove to ever prove it one way or the other.
Yeah, I'm at the point where I'm just like, more info is needed.
Right.
So,
more info needed to process this.
When I ran across this this photo of what he feels like the field of a conductor looks like, according to the dielectric and magnetic fields, and I just thought that was really interesting, and that's how I kind of feel like a lot of the way we view the world looks. And so I just wondered if maybe we're not looking down the barrel of a conductor at some point, and if light is kind of information processed through this conductor field. I don't know, man. It's a complicated thing. It's all guessing and guesswork, and this is a visual field map up in the upper right corner, and you just start to make some of these associations. But who knows the truth? We will find out one day, maybe, and maybe not.
Maybe not, and I'm okay with that. I think you said that in your video, and I totally agree with that. That I think I have to accept that not everything is going to be known to me by the time I take my last breath. So it's kind of listen to the information, get a good opinion of it, and move on. I don't think it's really important one way or the other. I just know that when I listen to people's explanations, the one that I can't jive with is the mass attracting mass, the planets becoming spheres, the spheres rotating other spheres. They're all doing so in a vacuum of space, but the vacuum of space is actually a field itself, and that it can be bent by massive object. That's where I just draw the line. It's okay, this doesn't jive with me anymore. But to most of the flat Earth explanations that we get, I see both sides and recognize the evidence that both sides brings.
I mean, if you're able to show mass attracting mass or something like that, or things throwing dust up in the air and it wants to clump together and become a sphere or whatever it is, or you can manipulate whatever you think gravity is, and you're able to manipulate it and then float people around, well, then you might have something.
Right.
But we don't really have that. So, and it's always funny to me, they always bring up Tesla's patents versus Einstein's patents, and right, that kind of argument.
Mm-hmm.
What has Einstein ever actually done for us? And it's an interesting argument that somehow we seem to think we know this gravity so well that we can slingshot, people through the universe, and Voyager all the way down out into the outer Kuiper belt or whatever it is. But we don't know. You can't show me a manipulation of it or any kind of way to affect it here on Earth, right?
Yeah, it's crazy. We know it so well. Exactly. That we do all these crazy gravity slings around planets and everything, and yet Neil deGrasse is asked about it, and he says, with gravity, we just don't know. We're confused. We're lost. Another super chat, thank you very much. Deliberate Creation says, just watched your video on quotes. We've been lied to. Well, thank you for that. Appreciate that. All right, sorry, go ahead.
Yeah, so I'll leave that aside for now. I didn't really want to get too much into that because, again, I think it's conjecture. This is total conjecture on my part. I was looking at this one too. When he puts two conductors together in proximity, what does that start to look like?
Yeah. Wow.
Well, I was like, shoot, it kind of looks like the equator,
Right.
but and star maps on the equator. Kind of weird, but again, it's just it's correlation, nothing more.
No, agree.
Who
Yeah.
knows? So what is a vanishing point? This distant thing that's off in the distance that's projecting all this information towards us, and we're taking it all and compressing it down and looking at the world the way we do. You can just take this hallway and you can transform it into this. There's no difference. Whatever it is, it's there, indoors and outdoors. But whatever it is, it's not this, right?
As I've said before too, when you go back, if you go back one slide just to the picture of the railroad tracks, and I tried to point out to people that what would happen on a moon. Let's say that we do live on a sphere. Let's say that the moon is a sphere. What would happen? Well, it would be this identical thing. That I think perspective would work no matter where you're at. If you're a globe believer and you say, oh well, we're on a big sphere, well then what would you think would happen on a smaller sphere like the moon? Would we still see things go to the vanishing point, or would railroad tracks go only say a third of this distance and then fall over the edge? Well, no, I think that perspective works the same no matter where you're at, especially on a flat surface.
Right. Yeah, they would think that at some point the railroad tracks don't meet.
Right.
There'd be a gap between the two railroad tracks because the curve would come sooner, and that just doesn't seem to be the case. So
No, not at all. It seems like perspective is what we see in the halving of our view, with half the information coming from the bottom up and the other half from top down.
So we know I know it's not this. It's not that thing. We know things get smaller as they move away and your horizon rises to eye level. You don't continually shift your eye level downward to see a falling horizon. Mm-hmm. And that was one of my points in the very first video I did, was when you look at all these Earth curve calculators and what they're modeling out, the observer is constantly looking down to see a falling horizon. And as they rise in height, and that it's just this, the whole thing, it just doesn't jive with me. It doesn't make any sense at all. So I hope people are able to understand that argument, that it's full of holes. It's not how we see the world. So
no, yeah. Earlier on my show today, I did a quick show just highlighting this one, and I was bringing up the McToon versus Austin Whitsitt debate. And, that guy McToon brought out a photo showing that the horizon drops, basically through like a theodolite app or something, showing that the horizon is below the eye level of the camera. And I showed pictures and videos from Sky Free showing that the same thing happens on a short distance, where he's got a boat off floating in no man's land, and the horizon is much lower than that boat, but we know that's not the real horizon, that the horizon is an apparent position. And so if the apparent position of that horizon drops a little, again, it doesn't tell me I'm on a sphere.
No, and I've done that one too with the airplane windows. I think we've talked about that one before, where you can see a potentially lower horizon out an airplane window. I've seen it, but then I've also been on planes where it didn't seem to drop, mm-hmm. right? Where you tape your phone to the side and you just take a bunch of still shots and so forth. So I've been on both sides of it.
Right.
But what I found one day, analyzing some of the footage, was that on the ones where the wing dropped, or where the horizon dropped, the wing was brought proximal. And so what is happening is, somehow, as this cabin pressure is increasing, as this plane goes up in height and the cabin pressure is increasing, there's some kind of bowing effect that's occurring to either the middle pane or maybe potentially parts of the outer pane. I wouldn't think so, but of these windows, and is adding a convex lens effect. Mm-hmm. And so I showed it on my stove, how that would work. So the horizon would drop and the things would be brought nearer to the observer, both at the same time. So, and I've done it now twice. So every time I've seen a horizon drop and I've been able to get the wing right next to me and do wing markers, the wing has also been brought closer to me. So, take with it what you will, but refraction, now I guess we're getting into this next part here, which I'll be really quick with, but refraction's a separate deal in my opinion.
Sorry to interrupt you. Are you showing anything right now differently, or move your mouse? I want to make sure my screen's okay. Good. I didn't know if the
Yeah, no,
my
I
screen
haven't
was
shown
frozen.
anything different.
Okay, just making sure. I heard you.
I don't have that. I don't have that presentation on this one,
No,
on this
that's good.
computer anymore.
I just
but
thought
it's
maybe
in
it
it's in
froze.
part 1 of 6. If they want to look at the plane footage, I analyzed Wolfie's footage and some of my own footage for the wing information. It was pretty cool. I'm proud of that one because I was just kind of eureka moment one day when I saw the wing markers and I was like, holy crap, the wing is coming towards me. And that's why the horizon is dropping. Anyway,
Right.
I don't know. You know how you're proud of some things and other people don't quite see it?
Yeah, it happens all the time. But it's like, all right.
Yeah.
What are you going to do?
Anyway. All right. So again, objects disappear bottom first along flat or uneven surfaces. That's what I'm trying to show with this lake footage. Has nothing to do with curvature. Your horizons vary based on your distance to tangible surfaces. In a concept for vision, the 3 reasons or the 3 kind of points of proof I would like to give were that we knew things get smaller with distance. We know that small things disappear. And when you combine those 2, you know that now small things disappear with distance. And the reasons that they can be due to can be a variety of things, and I list 3. And so the first one, which is just that compression rate of perspective, I'm trying to show here as to how that could cause things to disappear bottom first. The second thing would be a small obstruction within perspective in the foreground, meaning like something like a branch or a small wave or something is in the foreground, and we saw how that piece of debris rapidly rose to the midpoint of your vision. Well, if you put an object there, that had any height to it, it's easily possible that it could obscure something that's small and far away. And so that's what I was kind of showing here, and I did some math to show, like in the hallway, how high would something need to be this close to you to obscure the entire thing down the road. Well, this little blue thing represents about 1/4 to 1/3 of a golf ball, but you can easily see how that would obscure an entire golf ball further down the road. So that's that aspect. And then what about refraction? And this is going to be pretty quick here too. But this is I think Ranty talked about this last week, so I'm not going to go into this too much, but the Skunk Bay taboo conspiracy footage is great footage showing what things can look like. And I just took a bunch of stills and I put them together to see how they differ. And the lighthouse is the same position in each one. These are not expanded, right? They're just cropped. They're not blown up one way or the other. And so same thing. BML SB69 has been getting a lot of attention lately for the black swan argument, right? Have you seen that?
Oh, of course.
It's kind of going around. So, but he's great. He's been doing this for years, though. So I don't know if people realize that.
Right. I think
he's been doing these oil rigs. This was in my very first video. Was looking at his oil rigs,
right?
And the horizon line, how it changes positions, and that got me thinking about this issue of refraction. So where is the true horizon? Which one of these is true, right?
Right.
Well, globe people think it's this one, right? This is the true one, and this, where it's more distant, this is the false looming one. So you do have a problem there. How do you find out which one is right?
Yeah, especially because if you look at the lower left image again, I mean, according to globe believers, they have to believe that is a leading edge of a sphere. And so when you see horizon behind that, that's a big problem for them.
It's definitely not, because for one thing, just look at how big the waves are.
Right.
They're huge still. And we know that that's not how our vision works. This is an obviously refracted image, right? So anyway, but no, they'll say, yep, that's the horizon. That's the true horizon right there. That's 3 miles away from a 6-foot observer, and that's bunk. But my point with this is, where is the true horizon? It's actually hard to determine.
Well, especially a horizon is an apparent position. It's like we said, I don't think it's a physical spot. You can't go there. Obviously, if you start heading that direction, the horizon will move. So is the horizon even physical? Well, if you're on a ball Earth, that's what the horizon is. It has to be. It has to be what blocks distant observations. And if you believe in the sphere, that's exactly what it is. The horizon is the sphere edge. But if you
Yeah,
believe
I agree with you 100%. Let me rephrase.
Sure.
Where exactly is this oil rig? How about that?
Right. That's better
Right?
put. Yeah.
What's the true position of this oil rig in relation to my observer position?
Right.
Is it the one on the right, or is it the one, because they're in different positions, right?
Right.
So which one is the true one? That's a good question.
That's a good
Same
question.
thing here with the skunk base stuff. Which one is the true position of the mountain, right? Or the true position of the water or the lighthouse? That's because you're looking at it through this. Look at that. That's, to me, is what you're looking through, is these wavy water waves, right? So it can be doing all kinds of junk.
Which is what the atmosphere is. Yeah.
And then I ran across red pill stuff, and I've talked about this is in video 4, so I encourage people to go watch this video because I felt like there's a lot of good information in this. It's part 4 of 6 of that series, where I talk about upward refraction, and it's built on the work of others, right? Dr. John Dee, everyone who's kind of brought this information out beforehand, right? That it may be that we've gotten the direction of refraction in reverse, and that this is an upward refraction phenomenon causing this sinking, and it's not based on Edlin Sedor's or the modified equations that you plug in pressure and temperature gradients and you end up getting this light refraction index. I think they've calculated those. I think they've given pressure a little bit too much weight and not enough to temperature, but maybe that's kind of what I want to do for Appendix C or Appendix B or something like that down the road, is kind of tackle that a little bit more. But regardless of that, just based on a pure human intuition perspective, right? This red pill took this footage in January of 19 or 18, I can't remember. But it was a crystal clear day, no waves on this is ocean water. So this is a crazy good weather, right? And he did it when the air temperature and water temperature were essentially the same. Both were around 70. Because I remember when he put it out, and I talked to him the next day, and I was like, looking at I checked down where he was and what the air temperature was. It was exactly the same as the water temperature. But what he found on that day was awesome visibility. And he was able to see all these floors and the entire ground, right? Almost the entire ground, all this foliage that he'd never been able to see before. In all the other times he had gone out there, and he'd been going out there for months before this, taking the same shots and trying to see what he saw, right? So these are the ones in the red. These are the other times he went out and looked at this condominium complex.
Right.
And on the day that he goes out and gets this crystal clear, in my opinion, non-refracted image, he gets this, where everything is in proportion, right? So if you look at the actual condominium, this aspect on the top represents about 3 floors. And on this day, that's exactly what it represents. On all the other days, there's compression, there's rarefaction, things are stretched and pressed, and the positions of them in relation to the apparent horizon line is always different. So anyway, I use that to me is potentially a good baseline, right? So we're talking about where's the true horizon, right? Or where the true position of a building is in relation to your position. Well, you got to go find the right conditions. You got to go find the clearest, best conditions, and that's the most non-refracted conditions, and that's when you can say that's probably where that thing actually is, right? Does that make sense?
Absolutely. Yeah.
So this is, I saw Ranty on the show a week ago or so, I think it was. I was just watching it today. But this is kind of how this works. So I know this is a bit confusing when we talk about downward and upward refraction and what it's going to do and how the observer interprets this and everything. So what happens is the light ray comes in and it's bent upward to the observer. Okay, so you see this coming. This ray is coming down, right? Suddenly it hits a medium, right, and it gets bent upward and hits your eye at a slightly higher level than it would have normally. Does that make sense?
Yeah, but I mean, why would it bend up rather than down? Isn't it hitting a more dense?
Right, so that's the theory.
Right.
Is it hitting a more dense or less dense?
Mm-hmm.
So, in my opinion, it's hitting a less dense layer.
Gotcha.
I think that I think that there's less density down here on the bottom. And I think of kind of, I guess the Bernoulli effect, or not the, think of like an airplane wing where there's movement over the top of the airplane wing and causes less pressure and the airplane rises, right?
Right.
To me, that's what's happening on the ground is there's a lot of movement and things stirring and heat emanating from the earth and all kinds of things that cause a lot of kind of movement and motion from the bottom upward.
Mm-hmm.
And how cold air, rises, right? It gets colder as you go up in height. There are some,
right.
Layers of the atmosphere where it gets a little bit warmer and then colder, blah, blah, blah. But for the most part, where we see the world, it tends to be a little bit warm air rising phenomenon, right?
Absolutely.
And so that to me means that I have kind of less dense layers near the bottom. And there's a lot of articles actually that back this up, that at least to around 6 foot observer height, and especially over water, you're going to have a less dense medium. So what that's going to look like then is the observer is then going to straighten that information out. Whatever you want to call light, right? Whatever it is that's reaching your eye, the observer takes that information in and then assumes that it's all in a straight line, that it came to you straight.
Right.
And so they're going to press that thing down further in the distance. And so that's how sinking occurs. So does that make sense?
Yeah. Do you think that's the eye doing that or more the brain? That's more
the
of an
brain.
eye.
Sorry.
Okay. No, just making sure. Okay, gotcha.
Whatever's interpreting. But what's weird about it too, though, is it's not. Cameras do this too, right? So it's not that a camera doesn't do the same exact thing.
No, yeah. I mean, I think sometimes when I see these, disappearing from the bottom up when you got this water covering the bottom of the buildings, and I've showed it before and I'll have to do a video about it, where if I put a box down the floor of my hallway and then in front of me I maybe put some blanket or something, if I put a magnifying glass or any kind of magnifying sheet in between me and that distant object, it magnifies everything behind it, almost in the same that we were talking about with the 50% top, 50% bottom. And I think the magnification of that water sometimes covers the distant object. I'll have to show it again because it's hard to talk about without physically showing you what I mean.
Yeah, I know what you're saying. So you're saying that it pulls everything kind of towards the center?
Correct.
Right? Or pulls everything kind of near and towards the center and causes something to get obscured?
Right, because it's also magnifying the water behind that lens, right? And it's the same kind of deal. When we look out across the water, let's say we're looking 10 miles or something, that really, just like you can only see so much of that particular water, right? You've shown how what we're really seeing is a very short distance of water, and then it kind of compounds after that. And I think the atmosphere kind of works the same way. Really, if you're looking across water, the majority of what you're seeing, if you're talking about the atmosphere, is the atmosphere very close to you. And if that works as a magnifying glass, which I think have shown that does work, that is something that magnifies, then it's magnifying what's behind it. And what's behind it is the same. It's half water, half building. And if it kind of pulls them both together, I think that it covers the bottom of the building. Again, I'd have to show a
I totally understand what you're saying. What you can do actually, and I've done this, is you can take a Fresnel lens, like on what do you call it, on like a camper,
right?
And you get the little paste-on Fresnel lens, and it's just basically a lens that they've kind of cut into pieces and mashed together into a flat sheet.
Right.
You can take that and you can cut it in half, and then you can try to cut it in half right through the center, and then set it on a refrigerator, something really flat, super flat, and then put like a Coke can or something like that in the distance and see what it does to the Coke can.
Right.
And then flip the lens around the other way and see what it does. And it's going to press the thing lower, and then it's going to press it higher. And it's because of the direction of the little triangles that the Fresnel lens is made up of. So
right, like I think when we see these floors like we're looking at here on this slide, I think that whole view is a magnified view. I think when you do the math on distant objects, it seems like the buildings are always bigger to me than they really should be, and it's because everything that you're looking through a lens, and it's magnifying not only the building but the water behind the lens. which
Yep.
is
I
the
don't
atmosphere.
have a problem with that explanation at all. I think that Rob Skiba, I think, mentioned that too at one point, that he
Right.
thinks, it's the water droplets, and they all kind of
Accumulate.
coalesce
Right.
to get an effect that is kind of a giant lens. I think probably the predominant effect would be the half lens, more the density gradient issue. But I like both explanations. It's something we need to look into, right? I mean,
Absolutely.
so
Yeah, and again, I'm not saying that is the end all be all answer, because sometimes it's not there, and particular like this image here, where some days you just get a clear view across, but when the water rises, obviously the sphere isn't expanding. The sphere Earth isn't getting larger and smaller, causing us to sometimes see more and less buildings. But there is something changing, and that is the atmosphere between you and that distant object. So that's why I think that happens. But again, I also listened to Ranty last week. That was on last week's show. Anybody who wants to watch that, and I do kind of get this whole idea of refraction and the bending of that image up or down, depending on what the gradient of the atmosphere is above the water.
Yeah, I wanted people to keep in mind, though, so they don't get mixed up. Whatever direction the light is doing itself, before it ever reaches you, you take that and you straighten it out.
Right.
So it's kind of a world of opposites a little bit. So when people say, oh, it's downward refraction is looming. I just want to make sure people understand that. Downward refraction means you're going to see something higher than it truly is. So
Gotcha.
That's why I say maybe take a Fresnel lens and cut it in half and do it yourself, and feel the gratings on the lens to see which direction they're going, and then it'll all make sense. So
Gotcha.
So in this is the red pill stuff. I really like this because it's kind of a once in a lifetime footage that he got on that day. But this near field tree branch serves as the standardization, and then his position along the shoreline. And I use that to standardize the images without any cropping or expanding or anything like that. And then what you end up seeing is that when you perform that, the image 3, which is, so this footage here on the left-hand side, that was the crystal clear day, and I transposed that because it was the third footage that he took.
Mm-hmm.
The fourth footage was the day later. So this footage right here that I'm pointing to was just the next day after this one.
Right.
So that's how conditions can change.
And see, just like in that last image there at the bottom, this is what the McToon went out and said, oh, see, this horizon is lower than your eye level, therefore it's a sphere and it drops away from you. And I'm trying to explain, no, because it changes. Sometimes it's at eye level, sometimes it's a little bit below, but it's not because, what does he think, that the leading edge of a sphere is getting higher and lower each time? No.
Right. And so what I kind of determined for myself here was that when you perform this kind of crunch, I guess, between all these images, you'll realize that the horizon is the highest in the frame at the best conditions.
Mm-hmm.
And it's the worst conditions where it gets lower and you start getting things chopped off.
Right.
So anyway, I use the branch to kind of standardize all these and look at it that way. And the very worst one, it's by Grimmer, but is this one here, the one he took the day after. And look what you see. You see the inferior mirage now,
right,
which is something I've talked about as well. I know Randy's talked about that a lot. But in my opinion, when I see inferior mirages, I see the worst of this sinking phenomenon. So the argument is that this what I'm pointing to right now, well, that's the horizon, and then the buildings are actually contained within here somewhere. But I gotta disagree with that. I think this is still water. You're just not seeing it as water. You're seeing it as reflected, from above.
Right.
And the buildings are where they're at because that's how they've been presented to you, right? To your eye. That's the light that was presented to you. So, anyway, I'll leave that one there. But
that's good.
On that day, he on this great crystal clear day, and again, this is all in video 4, so I don't want to harp on this too much. I'm getting to the end here. But we were talking about black, and I know Bob talked about the blacks, how there's been multiple black swans out there, right? Mm-hmm. And I agree, there has been, and I feel like this was a good one that Chris came out with. So when he zoomed his footage out towards the Miami skyline, on that day, he was able to see forever. And so I took some of this footage and I kind of analyzed it and put it up against the landmarks that he was seeing. And what you find is that what should be hidden here is this entire building. You should never see this. This whole building should be completely gone, right? And people have talked about things that should be hidden and they're not for years now. But this is another good example, right? There should be
will always come back
geometrically, 130 feet is supposed to be gone. This thing's only 13 stories, I think, itself.
Right.
And if you consider looming to be, unobscuring parts of it, it's still 100 feet that should be obscured, and what ends up being is only about 30 feet worth.
Mm-hmm.
So there's all kinds of examples in this footage of that occurrence. So when he zooms around and looks at the cruise boat and the bridge and the Carillion Hotel in the background, you can analyze that all in one shot.
Mm-hmm.
And so what you end up with is the William H. M. Powell Bridge at 17 miles from Black Point, which is where he was at. There appears to be only about 30-foot cutoff, and that corresponds to about 1 arc minute of loss, strangely enough.
Imagine that.
Not 108 feet for that 77-foot tall bridge, right?
Mm-hmm.
You see a lot of this bridge, not 108 feet should be missing, and the bridge is only 77 feet tall.
Right.
The second thing in the frame here is the Carnival Horizon, which is over here in the left. It's docked at Dodge Island, which is 19 miles away, and about 35 feet is cut off. You can tell, right, because of where we can draw this line here, let's say, and that's the part that's missing. That's only about 3 to 4 decks worth. It's not, but if you do the calculator, the calculation, 142 feet should be cut off if it's refracted with looming, and then 170 feet if it's non-refracted. And this cruise ship is not that tall, right? So the cruise ship is, what is it? It's a 122-foot tall cruise ship. I looked it up. So again, another kind of black swan, I guess, whatever you want to call it, right?
Right.
Another great argument. The third is the Carillion Hotel and Spa at 25 miles, which only about 40 to 50 feet seems to be lost when not 270 feet. So again, all great arguments, against this whole idea that horizons are the leading edge of a sphere with an R of 3959.
Right.
We are getting too much obstruction near field, and we're not getting enough obstruction far field for that to make any sense. Does that make sense?
Yeah.
We're seeing too far for it to be a globe that way, and we're not seeing enough near for it to be a globe the other way.
Right. It's really well said. Haven't heard it quite put that way.
So something else is going on, and whatever that is, maybe we'll come to the answer someday. But so I guess what I started with was, why do objects disappear bottom first? And it could be a variety of reasons. You can choose one, but it's not because our horizon is the leading edge of a sphere, right?
Certainly
I think
not.
we can all agree on that. So,
well, I would love that if we did agree on that, but unfortunately, there's the globe zealots out there that are just going to continue spitting the same thing. They can't ever concede on anything. Where we could actually start to get somewhere if they would just concede that that's exactly what you just said. That
well, what's interesting? Someone in my comments on the video, a very well-known globe proponent on the circuit, if you will, said that I didn't prove anything with my observation. I didn't prove why the light disappeared, and I said, well, I never intended to prove why the light disappeared. I intended to prove that it didn't disappear because of R.
Right.
And then they said, well, things disappear bottom first because of a whole bunch of reasons. And I was like, what? Hold on, you gotta say that again, because that's a concession that I've never heard.
Right. Yeah, usually they say that any disappearance is earth bulge.
Yep. So,
yeah.
And again, I kind of reference these verses like this because I think it's important. There are some things in life I think that we're just not going to know the answer to. And I think God may have intended it that way, for us to kind of climb to the peak of our understanding and realize that we fall short. That to me is kind of the meaning of things, is to realize how little we actually do know, and not to have the hubris and that some people have, thinking that we've figured all this stuff out through science. And I think almost all of science at this point is bunk. anyway,
Yeah,
that's
can't disagree with
kind
you.
of
I
my
think
thoughts.
that they love to, and like I've said before, maybe we're not supposed to even know what the sun and moon are, but we're just supposed to stand in awe of the creation that is amazing. I mean, it's a perfect sky clock, and it tells us everything that we need to know, and just knowing exactly what it is or how it works or how far away it is or something maybe isn't for us to know, but there is a team of people out there that would love for you to think they've figured it all out. They can rewind the sky clock. They know exactly when the universe began. They can tell you the conditions of the universe, 1/1,000,000th of a billionth of a trillionth of a second after the Big Bang. And people will want to buy into it. Why? Because they worship man more than anything else. And so they love to hear men tell them that they've figured all these things out. They grovel at it. They just bow to it. Not me, not me.
Yeah, no, I think that's well said. That's a good sentiment.
So I appreciate you coming on. Thank you so much. And again, for people who haven't done so yet, go to Life is Short's channel. Subscribe there. As we talked about, go to Sky Free's channel. Go to Zachary Zabala's channel, Good Times for All. And, subscribe to some of these guys doing great work and great observations, and then come to your own conclusions. You don't have to believe Life is Short. You don't have to agree with his summary of it or what he thinks. You just need to be able to watch it and take the good and leave the bad. So check that out. And again, the angular resolution, perspective, and refraction with Life is Short video from April 11th, 2019. Definitely check that out. I think that was good. And so if people out there are interested in doing a presentation like Travis did today, or they have something different to present, reach out to me. Reach out on Skype. You can just search Jeranism Truth, say hello, show me what you want to present, either through a PowerPoint presentation or a keynote like you did today, or even just a video. It doesn't matter to me if the video has 8 views or 80,000. I'll watch it, and if I think people would like it or it's good information, then I'd be happy for you to join me and do an hour show like we did today and just present it. So coming up next week, we have Rodrigo. He'll be on my show doing basically a presentation on his new Spacecraft magazine, which I really like and want people to have a chance to take a look at that. Coming up in following Thursdays, we've got Iru, who's going to do his presentation from his Spanish conference in English on my channel. So all kinds of things going on. And if people want to join that or do a presentation, they can feel free to. It's easy, right? Life is short. You just have to come on, get in contact with me on Skype. We have a short conversation, set up a date and time, and boom, here we go. So
Jaren's a very good host. So two other people, Jaren, I want to make sure to if people can check out the Buzz Dev on his channel.
Yes, thank you.
And then another one too, which I saw today doing a live stream, and I was watching. I was like, man, he's coming out with some really good stuff lately. And I'm on like a small Skype chat with him too. Is Heath Carmody, and he has a great calculator that he's been working on. It's pretty complicated or complex at this point, but it's really well put together. And so he's doing a lot of work on refraction and kind of modeling in 3D a lot of the images that we see, and kind of going through this upward and downward refraction issue. So Heath Carmody, the Buzz Dev, Dr. John D., and all the other folks that we normally talk about as well. So don't want to miss anybody.
Great. Any final words, or tell people what you have coming up or what to expect on your channel? Or
no, like I said, I'm probably I wanted to finish kind of appendices or just maybe going into in-depth a little bit on each thing that I think is a good reason why obstruction occurs.
Cool.
So the next one might be on refraction and kind of going into Edlund-Sedor and some of these other formulas. But the hard part about some of that is you kind of need laboratory settings to prove, or prove or disprove one way or the other that pressure needed to be this in order to bend light this much, and temperature needed to be this, and that part can be a little bit hard, but maybe more a retrospective thing on some of the literature that's already published.
All right. Well, whenever you get around to that, you're always welcome here to present. I would love to have you back, so I really appreciate you being here.
Yeah. Have a good one, Jaron.
All right. Take it easy. All right, guys. That was Life is Short. That was our presentation for today. Like I said, tune in Thursdays is my hope. I can't guarantee you it'll always be on Thursday because it kind of depends on when other people can do it. But I do think next Thursday that Rodrigo will be able to be on and present some of his Spacecraft magazine. I think the following Thursday possibly Iru will be on. And, of course, check out tomorrow. What is tomorrow? 14, Valentine's Day. Ooh, fun. We'll have another Jeranism Friday Lounge, which is just kind of a kickback, fun place to hang out. and talk, which we'll be doing that. So feel free to join us in the chat there. And as always, just keep watching my channel for more and more Jeranism Raw. If you want to watch Monday Night Show, that's also on tfrlive.com. This last Monday, we had Crow 777 jump on. We had Owen Benjamin jump on. We had Jason Lindgren on with David Weiss and I. It was a fun show. I think people enjoyed it. So check that out if you want. You can also find that, I think, on DLive, as most of my shows are up there for 3 or 4 days, however long it holds different shows. So hope that was fun for everybody. Maybe I want to check one other thing here. Let's see here. Somebody told me about, see if we have any money in the chest. People told, oh, not very much in there. Sorry. People said I should release this little chest whenever I'm done with the show. Let's do it now. Distribute rewards. There you go. Submit. Psh. There we go. I just added 50. Oh, wait. I added 50 lemon to the chest. That's not what I was trying to do. Great. Now I probably screwed it up. How do you... Oh, distribute rewards. Boom. Oh, now somebody else says let the chest build. Sorry, this giveaway is too close to your last one. Please wait and try again later. Oh, well, now I can't even do it. All right, I'll let the chest build, and then I'll give it away. I don't know what I'm doing here on DLive. No idea. So that was fun, guys. I remind you to do your own research, because when you do, you'll never again believe what you've been taught. This has been Jeranism with Life is Short. Hope you guys enjoyed the presentation, and we'll see you tomorrow for another Jeranism Friday Lounge. Also, a final shout out to all my patrons. And if you want to join them, patreon.com/Jeranism. If you want to send some tip, you can do so through Venmo at Jeranism, or you can use Cash App too at Jaron Campanella. But that's about it for those options, but would appreciate it if you became a patron. And if not, just share the show, like the show, give it a thumbs up if you like it. And if you don't like it, find my channel and hit delete or block or whatever you need to do so you never have to see my stuff again. Isn't that the best way to police yourself? I think so. All right, guys, it's been fun, and see you tomorrow for Jeranism Friday Lounge. Till then, this has been Jeranism. Peace.